Welcome to The Explainer. Today, we're diving into a fascinating microscopic secret, a secret that explains how one piece of steel can be 5 times stronger than another. This isn't just some tiny detail. It could completely change how we build some of our most critical infrastructure. So that's the big question we're tackling today. How is that even possible? It's a mystery that starts with 2 simple-looking pieces of steel, but the answer takes us deep, deep down into their atomic structure. And it really shows how the tiniest details can have the biggest impact.
All right, so first things first, let's set the stage here and figure out why this matters so much.
Okay, so the big challenge is all about making our power plants more efficient, right? And to do that and cut down on emissions, the steam turbines inside have to run hotter and at way higher pressures than ever before. Now you can imagine that puts a ton of stress on the metals they're built from. And the solution engineers came up with is actually pretty clever. See, instead of building a whole giant turbine rotor out of one super expensive metal, they decided to combine the best of both worlds. They used this advanced 9Cr steel, which is amazing at high temperatures, for the hottest parts. But then, for the other sections, they use a different steel, CR-MOV, which is still great but a lot cheaper. They basically create this hybrid rotor. The only catch? They have to be welded together perfectly.
And that's where the real engineering puzzle comes in. This weld right here, this 20mm thick seam joining 2 totally different supersteels, it has to be flawless. I mean, literally, the safety and the efficiency of the entire power plant are riding on this one connection.
So, to figure this all out, researchers at Shanghai University set up a kind of showdown. They took 2 cutting-edge welding techniques and put them head-to-head to see which one was truly the best for the job. The 2 contenders are called NG-SAW and NG-TIG. Now, you don't need to memorize the names. The important thing is that both of these are really sophisticated, top-of-the-line ways to weld thick steel. Everyone expected them both to do an amazing job. So, how do you find out which weld is tougher? Well, you try to break it. Scientists use something called a Sharpie impact test. The idea is simple, but pretty brutal. You've got this heavy pendulum that swings down and just smashes into a sample of the weld. The test measures how much energy that piece of metal can soak up before it snaps. It's a classic way to measure toughness. And this is where things get really weird. The results weren't just a little different, they were shockingly different. Get this, the NG-SAW weld, it absorbed about 29 joules of energy. Okay. But the NG-TIG weld, 154 joules. That is more than 5 times tougher. Nobody saw that coming. A difference that huge was a total surprise. So yeah, this was a genuine shock to the scientists. How could 2 top-tier welding methods give you results that are so far apart? This is what kicked off a deep dive investigation, kind of like a forensic analysis, to look at the microstructure of the steel and figure out what on earth was going on. Okay, so the first place they looked for clues was the most obvious one. What does the basic structure of the metal actually look like under a microscope? And here's the first big twist in the story. When they looked, the welds looked, well, pretty much identical. You can see it in these images. Both of them show this structure called tempered martensite, which is exactly what they expected. There was nothing there, no obvious clue that could explain that huge 5 times difference in toughness. So their first big lead was a total dead end. The mystery just got deeper. Okay, the researchers thought, if the main structure is the same, maybe the hardness is different. That seemed like the next logical place to look. But nope, another dead end. They measured the hardness all across the weld for both samples. And as you can see from these graphs, the profiles are almost a perfect match. So at this point, the mystery isn't just deepening, it's becoming seriously baffling. With all the easy answers turning up nothing, the team knew they had to go deeper, much, much deeper. They had to look beyond what any standard microscope could show them. They started to realize the answer wasn't in the big picture, the overall structure of the metal. It had to be something much smaller, hidden inside that structure. So they brought out the big guns, a scanning electron microscope. And there it was. Finally, in these images from the weaker weld, you can see these bigger, kind of clunky particles. But look at the images from the super tough weld. The particles are way finer, and they're spread out all over the place. This was the smoking gun they were looking for. So what are these little dots? They're called second-phase precipitates, Basically, as the weld cools down, these tiny little crystals, in this case they're rich in chromium, form inside the steel. And it turns out their size was the secret ingredient, the hidden variable that was controlling everything. Okay, so mystery solved, but why? Let's dig into the science of why the size of these tiny particles makes such a huge difference in strength.
I love this analogy here. Think about reinforcing concrete. If you just throw a few big rocks in there, it's not going to be very strong, right? But if you mix in fine, evenly spread sand, that concrete block becomes incredibly tough. It's the exact same idea with the steel. Those tiny, fine particles in the tough weld act like millions of little anchors. They stop tiny cracks from even starting or from spreading if they do.
And this drawing from the study shows it all perfectly. Take a look. In the top row, that's our weaker weld, those big particles actually become weak spots. When there's an impact, little voids and cracks start to form right around them. But now look at the bottom row. With all those fine particles, the structure just holds together. It resists breaking apart. It's a brilliant visual. So here's the bottom line. The secret is the cooling rate. The NG-TIG welding process cools down faster, and that doesn't give those little crystal particles enough time to grow big. So you end up with finer particles, which means you get tougher steel. And what does that mean in the real world? It means safer, more reliable, and more efficient power plants for all of us. You know, this whole investigation is just such a cool reminder that sometimes the biggest differences in how things work, whether it's a giant turbine or anything else, it all comes down to the tiniest, most invisible details. The answer was hiding there the whole time. They just had to know where to look. And more importantly, how deep.